have a box. Let's put it here. Let's say I have a box sitting on the ground. So this is the ground. And this is some rough surface. It's not smooth, so I cannot ignore friction. Well, see, it's asphalt. I have a box there. It has some weight. Right? So it's, let's say the weight is W, and it's pushing the box downward. So I'm just going to put it right here like this, W. And I'm trying to push, or better to say pull this box, right, with some force. Here is my force. Let's say I'm trying to pull this direction with some force. I'm going to call that force P. Right. Now, obviously you have experienced that. It's not that easy, especially if the surface is rough and the box is heavy. It's not that easy to pull the box, right? And it's not just because the surface, the box is heavy. It's also related to the way the surface of the box and the floor are having their contacts with each other, depending on how rough the surfaces are. Now, we want to take a closer look, right, at the contacting surfaces, right? I want to zoom in. Think about it this way. I want to zoom in here. And look at these two surfaces closely. If you really have a microscope, you can zoom in and look closely what happens between these two surfaces. You're going to see something like this. Let me see if I can draw it here. This is part of that surface. So I zoomed in, right? So since I zoomed in, it's not going to be very straight, probably. So this would be, your surface could be something like this. I can probably do a better job. Right, this is your surface. And it's, the box, right, that side of the box probably looks, you can think about it like this. Right. This is when we really zoom in. So there are so many points of contact. We are looking at this in a microscopic level. Right? So many microscopic irregularities exist between these two surfaces. As a result, there are forces. You can think about each of these as a point of contact. Right? So at this point, remember, at any point of contact, we have a normal force. Right? This is something we had from before. In a contact, when two surfaces are in contact, we have a normal force. So I put, maybe it was a different color. I put a normal force there, another normal force there. Let's say we have a contact here. Another contact, let's say there. And I purposefully, on purpose, I'm making them different sizes. Let's say size represent how strong the force is. Since the force is applied to the right side, we have more pressure on the box closer to the right side. And so let's call these, I'm going to call these normal forces. Let's say call them delta N1, delta N2, delta N3. These are just normal forces. Delta N, as many, N of them could be there, right? Let's put it this way, saying there are more. Delta N. And for any, at any contact point, right, the friction is trying to oppose this motion. Right? So let's also put those here. Let's say this is friction, this is friction, this is friction, this is friction. Right? We said that's friction. That's what it does. if the box is going to the right or if it's about to move to the right, friction should be tangent to the surface, right, at points of contact, and should oppose the direction of the motion, so to the left, all of them, right? Again, this is microscopic level, so I'll call this, let's call this delta F1, delta F2, delta F3, delta Fn. So at any point of contact, you will get a resultant force, right? At any point of contact, you have delta F to the left, delta N upwards, so we get some resultant force, right? I think I mistakenly, there you go. So we get some resultant force. I'll put those resultant force in this way. I'll call them, let's call them R, delta R. Delta R1, delta R2, delta R3, delta Rn. And again, this is a microscopic level. So we have some reactive forces. I want to think about these R values. Are developed, these reactive forces are developed at each point of contact. Now we have so many of these, right? This surface. This is a microscopic view. Zoom out, there are so many of these points of contacts between two surfaces in a macro level. But generally, you can think about this as delta R, right? Is delta N in normal direction. I can write it as En plus delta F in tangent direction, Et. Right? Normal direction and tangent direction. That's a general idea about this reactive force. Now, this reactive force is basically friction. The combination of normal force, well, the delta F's are friction. You have normal forces, so it develops some reactive force there for you. That's what you have when you are dealing with two surfaces with friction between them. Now, now if you want to actually look at this in a macro level, if I draw this, that's basically what we do. We don't really go into microscopic level. We don't care about irregularities between surfaces to that level, right? We want something more general. You can think about it this way. If you draw the free body diagram for this box, you're going to end up having, well, your weight is there. Box has some weight. You're pulling it to the left, to the right, sorry, with force P. You have your friction force there. I'm using different colors. Right there, right? Tangent to surface, opposing the direction of the motion to the right. So let's call this F, friction. You can call it FK. We'll use different naming for this. We call it FK, FS. I'll talk about that. But generally speaking, let's just say put F here as your friction. And then you have the normal force. Now, the thing is, since we don't know, going back to microscopic level, since we don't know which one of these points have stronger reactive force, right? This is a microscopic level, so depending on what the friction, which point is resisting the motion more than the other, because it really depends on the way the surface is, the surface looks like, the surfaces look like, and also depends on where this force P is applied. Obviously, if you pull this box to the right, you can probably feel it when you're pulling a box or you're pushing a box. If you have a box like this, right? And I could do a better job than that. If you have a box like this, I'm just giving you some intuitive I'll try at least to give you some intuition about what happens there. If you push it from the top, right, there is more tendency for this box to roll over, right? So there is less force here, and there is more normal force applied to the box in here, because then what happens is that it flips over. If you push it from this part, like closer to the surface, right, it keeps going straight. So we don't really, it's not that easy to figure out where should we put, that's what I'm trying to get to. It's not that easy to figure out where should we put this friction and the normal force on the box, right? Where is the point that we should decide to put this, right? This box has some width. Let's say a box has a width of 50 centimeters. Well, the question would be, should I put this force, this friction force? Let me see if I can clean it up without. Where should I put that, right? I know I have to put friction force F and normal force somewhere. When we were dealing with particles, normal force, we could just put it anywhere. And also when we didn't have friction, right, we were less concerned about this. And when we had just one point of contact. But if we have the whole surface on a floor and we have friction, now the question would be, where should this point be? This point. Right? Should it be here, here, in the middle, here, closer to the left? That's something that is actually unknown. Because as I said, depends on where we apply the force P, how far up, how close to the bottom, what is the irregularities on the surfaces. So we actually don't know where we have to apply these forces. This is something that we have to actually figure out. So when we draw the free body diagram, here's what we do. We say, well, here is friction. Here is the normal force, which together they create this reactive force that is resisting the motion, like this R, N here. And this point, I don't know where it is, this point. So the way we deal with that, we say, well, since we don't know where it is, we are going to draw a line. Let's say we take a reference, either all the way to the left, somewhere that we know. If, let's say, typically what happens is that we say, well, if this is passing through the middle at this line, I say this point should be somewhere X away from the center. You could just say, you could take another reference. You could say you take the reference on this corner of the box and take this as X. The logic, the general idea is that you don't know where this N and F and together this reactive force, these are two components of the reactive force, or where does it apply? Where do you have to apply? Where you need to apply this in a free body diagram? So not only the friction you don't know, or depends on what information you're given, it might be a known force, but where this friction or this reactive force should be applied on your free body diagram is unknown. That's something you have to find that out when you're dealing with a rigid body, that the contact between two surfaces, you have contact between two surfaces. If the contact of your rigid body was just at one point right here, something like this, you already knew where to put it, right? This would have been your friction, this would have been your normal force. But when you have surfaces in contact with each other, where this friction and normal force should be applied, something that you need to figure out, or we need to figure out using equations of equilibrium and the information we are typically given. So we will look at examples and you'll see. Just keep in mind that something that's unknown, right? Just take it at some distance from some reference. All right. Now, this is basically from going from microscopic level to macro level and figuring out how to basically put friction on your rigid on your free body diagram when you're drawing a free body diagram for rigid body, right? When you have two surfaces in contact. So remember, you have friction, you have normal force, but where does that friction have to be? and normal force have to be on your free body diagram is unknown. All right. And then next, let's talk about the magnitude of friction, right? That's what we're basically getting at. That was like an intro to what this friction is and how to put it on a free body diagram, because we need to know that. Then we'll talk about what is the magnitude of this friction and how can we find how far or where should we put it, right, when we draw a free body